One of the chief questions you may now be asking yourself, since we've seen that we can combine together temperature, concentration, and pressure to truly understand when a reaction might be spontaneous, is how do you actually measure this in the lab? To do that, we can take advantage of the nature of this function. That is, the idea that when a reaction is at equilibrium, a condition that we can measure in the lab, it has a direct relationship to delta G naught. So there are a couple things that we can potentially do with this that are pretty useful. One is to recall that delta G naught is also equal to delta H naught minus T delta S naught. We can do some very useful rearrangements by letting these be equal to one another. We can now divide both sides of this reaction by RT. The result from doing that is that we now have minus delta H naught over RT. These cancel, so we have delta S naught over R equaling ln of KEQ. Let me rearrange this for you again, just a little bit. I'm just pulling the 1 over T out. This looks quite a bit like the equation of a straight line. What this is telling us then is that if we measure the equilibrium constant of a compound, and remember that equilibrium constant we're getting just from concentrations or pressures, the sorts of things that we can measure in a lab using any of a variety of tools, things like pH or UV visible spectroscopy. If we measure a variety of equilibrium constants at a variety of temperatures, we can plot the inverse of the temperature versus the natural log of the equilibrium constants we found, and it should give us a straight line. That straight line should meet the vertical axis at delta S over R, and it should have a slope of minus delta H naught over R. So throughout this semester, I've been telling you that we relied on the hard work of graduate students past to understand the delta H and delta S values for a variety of reactions. Well, this is the primary way they did it. This is one of the useful approaches that can be taken to understand chemical reactions. But there's a little bit more that we can do with this expression. That's because we could take a particular set of KEQ values, that is a particular set of temperatures and KEQs, and combine them together to get another quite useful equation. And that equation looks like this. The natural log of the ratio between the equilibrium constant at two different temperatures is equal to delta H over R times temperature 1 minus temperature 2 divided by temperature 2 times temperature 1. This equation is a quite straightforward way to ascertain the delta H of a reaction from a pair of temperatures and KEQ values. So as you can see from these equations, we can use the relationship between our Gibbs free energy equation and KEQ to have a variety of experimentally accessible approaches to determining these values for ourselves.